Introducing first Team 871, the West Islip Robotechs. Here at West Islip High School, we design, manufacture, program, and test robots to play in the first robotics competition. My name is David Mahany, and today I will be showing you how our team operates, some of the challenges we faced this year, and how we have solved them. Team 871 is split into 5 subteams, each serving an important role in the creation of our robot. The CAD team uses computer programs to design parts and put together the robot digitally so we can test new designs without having to physically manufacture the parts. The mechanical team is responsible for prototyping, manufacturing, and physically constructing the robot. The electrical team designs and creates the electrical board and all of its components, and hooks up any sensors, motors, or pneumatics needed to control the robot. The software team programs and tests the robot, and also designs the dashboard each year. The business team organizes fundraisers and coordinates our community outreach. Each subteam has one or more adult mentors, as well as a subteam captain. The subteam captains are responsible for managing their subteam and report to the team's systems engineer, whose job it is to coordinate and communicate between the different subteams. We find that this organized leadership helps greatly to keep the team on track. After switching to it a few years ago, we found that we are able to better work as a team when everyone has more organized roles. Once the season's game is revealed, the team enters our initial design phase. The whole team gathers to learn the rules and brainstorm strategies and high-level designs. We use a top-down approach during this phase to make sure we don't get too specific right away. We also make sure to include everyone so we don't miss out on any good ideas. After we have considered our options, we vote on which type of robot we want to make. This year, we chose to make a robot with a 2-segment arm and wrist, with controllable vacuum plungers at the end. The motors and potentiometers at each of the 3 joints would allow software to move the arm to any position in the 2D plane of the arm. We would later realize a large difficulty with the arm is controlling it, as you would need to control 3 joints and 2 vacuums all at once, both precisely and intuitively. A few members were thinking of control systems, and someone suggested making something that attaches to the human driver's arm. It would be a wearable 2-segment arm with sensors at the shoulder and elbow, which could be used to control the robot's arm intuitively and precisely. For the wrist, we decided adding a 3rd segment would be less beneficial, as a mount to the human wrist would be harder to make, and we needed some way for the controller to turn the vacuums on and off. In the end, we decided to use a Wii nunchuck controller, as it provides inputs to control the wrist and vacuums, and can be held comfortably with one hand. As a starting point, we made a CAD drawing of the general shape of the arm, and a wood prototype was laser cut to get an idea of how well it would work. Around this time, we also tried out an alternative, a simplified tabletop model of the robot's arm using software to directly map the model to the actual robot. One benefit was that we could use the same software as for the worn arm, allowing us to debug several layers of software early. Eventually, we began work on a more complete version of the worn arm, which included improved mounts and was better fitting. This version is metal to help durability and uses elastic straps to secure it to the driver's arm. After we decided to use the nunchuck, I began thinking about how it would work. Since the nunchuck uses a proprietary connector, I wanted to replace this with a more useful USB cable. In order to do this, I would put a microcontroller inside to read from the sensors directly, and that we could feed in the arm's sensors to simplify the electronics. I drew up a simple diagram, and the next meeting I began work on the wiring. In order to simplify the setup, the wires ran out of the nunchuck so I could more easily manipulate them. While at first I used any available microcontroller, it would be too large to fit inside of the nunchuck. We soon found a tiny microcontroller that would fit, but there was a problem. It wouldn't have enough pins for all of the sensors we needed. To solve this, we realized we could mount 2 on top of each other and allow them to communicate, which would make enough pins available. After a few final tweaks, we were able to test the arm and nunchuck in full on the actual robot. Right now, we're working on making the arm more comfortable and moving the microcontrollers back into the nunchuck, which we believe will be relatively simple. In terms of software, there are several layers of systems that were needed to get the arm working. The 2 microcontrollers are mounted on top of each other, with some pins connected through, allowing them to communicate. The 6 sensors are each using one of the 6 available pins spread across the 2 microcontrollers. Using software I wrote, the bottom controller sends updates to the upper one, and the upper one sends the combined data over USB to the driver station computer. The dashboard runs on the driver station computer and is one end of bridging the gap between the laptop and the robot. Reading the serial data from the USB, it pipes the received input into a virtual joystick that the robot can see through the driver station. The robot code first transforms the axes from the joystick back into actual angles. Initially, we simply used these angles to directly drive the arm segments of the robot. However, this simple system could not be used to limit the robot's extents as the rules require. Our solution was to implement 2-way kinematics into our code. First, the angles are used to calculate the endpoint of the arm using forward kinematics. Then, we apply the maximum extents on this endpoint and use it to solve for the 2 new angles using inverse kinematics. The new angles can then be used as set points to drive the arm segments. While this may slightly break the immersion of using the arm, we believe this is the best solution while keeping it legal in the rules, since it will still preserve the height that you're trying to reach. I have certainly learned a lot as a member of the team. Working on this year's robot, and especially the power arm, has felt like a sort of final test, challenging my peers and I to push ourselves to create something amazing. Without the support of FIRST, as well as all of the mentors and volunteers, we would have never gotten this opportunity. In the future, we hope to continue to spread our enthusiasm at competition and beyond through the process of cooperation. Thank you.